Okay, well, hello. Welcome to my talk at FSE 2022. So this is a journal first presentation. The paper was published at IEEE TSE earlier this year. So I'm Ellen. My co-authors on this work are Max Schaefer at GitHub and Frank Tipp, my PhD advisor at Northeastern. So I'm just going to present kind of a background motivation for this work. So JavaScript is a highly dynamic language. And it's dynamic in a variety of ways, but the one we're going to be focusing on here is event-driven programming. So what is event-driven programming? Well, basically, it's a message passing system that triggers asynchronous computations. So a good example is you have a website, you have a button. When you click it, you want it to do something, but you don't want, you basically want it to be a reaction. So you hear the click event, and then you do the reaction that you want to happen on click. So here's an example of what the code looks like. We have an import of the HTTP library, and then we have the registration of an event handler on the request object for the event name response. So response is a free-form string with 0 checks because JavaScript, and the function here is just a callback. So this is the function that gets executed when the response event is heard. It's also important to note that users can admit and register listeners for any arbitrary events that they want, no restrictions. The event's just any string. So in this work, we use the size of the JavaScript ecosystem to our advantage, and we show that we can run a simple static analysis over a large amount of code to mine application-independent representations of these listener registrations. And then looking at the results altogether, we can use the data to identify bug patterns. So we are using a statistical analysis to find dead listener errors. So first, let's break this down. What is a dead listener? A dead listener, probably best explained by example. Here's a giant pile of code, but we're going to break it down. And also note, this is taken from like an actual project on GitHub. So here we have a HTTP server response. First, we see 2 listeners. So we see a listener for the data event and a listener for the end event, and these are totally fine and they work. And this is the intended usage of the server response API. And then we see another registration which totally blends in, but it's wrong because the response objects never emit timeout. So this is dead code. It will never be executed because there just is no emission of this event. And so this is a bug. And this is a hard kind of bug to find because there's no crash. The only thing that happens is that this code doesn't run. So here's a diagram overview of our approach. We're gonna, basically, we start with the mining through static analysis of these application-independent listener registration pairs. And the representation of these pairs is what I'm gonna explain next. So we use access paths to have a code base agnostic representation of the object on which the listener is registered. So this is just the grammar for access paths, but I'm going to explain it by example. But basically, it's like the sequence of computations on the import of the library that we use to build the object at hand. So if we look at the server response object from the last example, this is the access path that represents it, and we can see why this is the access path. So this is the first argument to the second argument to the request call on the import of the HTTP library. So it's always rooted in the import, and we see like the HTTP object is just the variable that stores the import of the library. There you go. So our classification stage is where we see the statistical analysis come in. And this is based off of the assumption that we expect most common API usages to be correct. The classification is based on rarity. So we have to quantify this idea of rarity. We're saying a listener registration is rare if the event is rare for an access path and the access path is rare for the event. So basically, they're both rare for each other. And we compute rarity using the binomial cumulative distribution. So for an access path, AE, where we see NE occurrences of pairs that have the same event E and K occurrences of that specific pair, then we consider A to be rare for E if the following formula is true. And we're going to break this down into its component parts. So we use the binomial cumulative distribution function. This computes, well, I'll explain the variables in here. So KE, the first argument, is the number of occurrences of outcome E of an experiment that has two possible outcomes, because binomial. P is the probability of any one of these experiments being E, and then N is the number of experiments being performed. So if we put all of these in to the binomial cumulative distribution function, the output is the probability of observing at most KE occurrences of E over N experiments, where the probability of E being the result is P, and the experiments are independent. And this last part is important. It means that the outcome of one experiment has no influence or effect on any future experiments. So a classic example of this is coin flip. So here we see, we can use an example to explain what this means. So what is the probability that we see less than or equal to 2 heads over 10 coin flips? We can use the binomial cumulative distribution to compute this. So here we have at most 2 occurrences of the outcome heads over 10 experiments. We know the probability of getting heads in a fair coin is 0.5, and we know the experiments are independent. So we can just put all these numbers in and we get this result back, which is interpreted as there being a 5.47% chance that we will see less than or equal to 2 heads. And we can also interpret this as saying, well, this means that we're 100% minus 5.47, so 94.53% confident that we will see more than 2 heads. And it also means that if we did expect that there should be only 2 heads over the 10 tosses, then the confidence means that the probability of getting heads in any given toss is less than 0.5. So we can use this reasoning to represent rarity of access paths for events and vice versa. So as an example, we saw the bug in the code base before, the listener registration for timeout on the server response object. So let's see what happens if we look at the results from our actual data. So in our data, we see 216 occurrences of the event timeout. Only 2 of them are on this pair. And again, we're considering E to be rare for A if the binomial cumulative distribution function is true for these specific thresholds, the rarity threshold, PA, and the confidence threshold, PCA. And these are parameters. We don't know what these values should be. So imagine we choose PA to be 0.05. So that would mean we're considering rarity if it's less than 5% of the time. So if we see this event less than 5% of the time on this access path, then it's rare. So in our case, then we would plug this in and we would get 0.001 back. And we're assuming that our data is a representative sample. So that means that we're 99.9% confident that the actual occurrence, like the probability of getting this event for this access path is less than 0.05. So if we're saying that something's rare, if it happens less than 5% of the time, then that means that we're very sure that this is indeed a rare event on this access path. We talked about how event has to be rare for access path and access path has to be rare for event for something to be considered rare. So we just do the exact same computation for both and then add the results together. And if they're both true, then we would consider the pair itself to be rare. Our statistical model has 4 parameters, so the 2 rarity thresholds and the 2 confidence thresholds. And we don't know what they are. So our experiment was to find an optimal parameter configuration. Given a particular configuration of the parameters, we would pass this into our classification algorithm and then get listener registration pairs back that are classified as being incorrect. So that's basically the approach. Now the results, we looked at 4096 model parameter configurations, and then we ran the same experiment for all these configurations over 532,000 pairs mined from 127,000 GitHub projects. We defined an optimal configuration to be that with the highest recall and a precision of at least 90%, where recall is the percentage of known bug patterns. So basically, how many results And then the precision is the percentage of bug patterns that the analysis finds that are known to be bugs. So basically the accuracy of the results. We validated this with a semi-automatically generated validation set. And if you guys have questions about how that works, feel free to ask me. But basically just we needed a set to compare the results to see how well basically how well the approach worked in terms of actually finding bugs. And with these definitions, we found that the optimal configuration is both rarity thresholds are 1%, confidence thresholds are 3% and 1%. So with this optimal configuration, we found 75 listener registration bug patterns with a precision of 90.9% and a recall of 7.5%. We looked at a bunch of instances of these bug patterns in actual code. And through this, we reported 30 actual bugs to developers. One of them is the example that we used at the beginning of the talk. There's a few limitations to this approach, of course. There's bugs in rarely used APIs are missed, and rare correct usages of common APIs are often flagged as bugs. The takeaway is that it just doesn't work very well if there's sparse data. But yeah, anyway, that's all I've got. So if you have questions, now's the time. And also I'll be at the conference, so you can ask me then. Peace.